Okay, so we were talking about quadratic functions in standard form, right? So we learned that a quadratic function in standard form is just the form ax squared plus bx plus c, just a different way of writing quadratic functions. We reminded ourselves that all quadratic functions, when I graph them, they always give us parabolas, right? U-shaped parabolas. But we have to figure out, what does that parabola look like for any given function, right? Okay, so we know a couple things though. We know that when A is positive, right, A is the same in standard form as it was in vertex form. A is the vertical dilation factor. So when A is positive, the parabola is going to open upward. When A is negative, it's going to open downward. It gets reflected and it opens downward, right? Okay. We know that if a parabola opens upward, then the vertex ends up being the lowest point on the function, and that represents the minimum value of our function, right? The minimum y value, okay? If a parabola opens downward, then the parabola becomes the vertex becomes the highest point on the parabola, and it represents the maximum value of the function, the maximum output or y value, right? Okay, and we were able to graph quadratic functions in standard form by really just kind of cheating in a way and using the same technique we used with vertex form. The only difference was we had to calculate the values of h and k this time, but we have some little formulas that allow us to do that really easily, right? We know that the x coordinate of the vertex, which we always call h, is given to us by the little formula negative b divided by 2a, right? And once I know what h is, I can always find k, which is the y coordinate, by just plugging h into the function, right? That's always how I find a y value if I know an x value, okay? So then today we get to do something that I think is pretty cool. And I want to just take a second. I want to prep you for this. I want you guys, it's really important, in anything, if you want to learn something well, this is the best advice I can give you in life about how to become good at anything in the world. All it takes to become good at something is you have to be able to just trick yourself and inspire a little interest on your own part, right? I mean, there are things, this is kind of a grim thing to think about, but would everybody just pause and consider this for a second? How many of you have a chore of like taking out the garbage, right? Something like that, some chore that you really don't care for. How many of you guys take out the garbage or do something equally bad for a chore? Tell me yes if you do. Everybody has a chore that's either taking out the garbage or just as bad, right? I mean, when you're doing that, like when you're taking out the garbage, aren't you just looking forward to getting it over with, right? And getting on to something that's more interesting, right? I get that. But let me ask you this now. If you found out tomorrow that you only had 2 weeks to live, wouldn't you, even those times that you spent taking out the garbage, wouldn't you even want that time back? I mean, wouldn't that be something like, that's still time that you spent, right? I mean, you would say, man, if I could just have that time back, I would appreciate it more, right? I mean, you could make an art out of taking out the garbage if you really wanted to, right? I mean, you could consider how to do it, and you could become the best in the world at taking out the garbage if it's something that you really put a little time into. I'm not suggesting that's something you ought to do, but there's some value in everything we do, right? During our lives on earth, our finite lives on earth. We're not here forever, so you got to make the best of every second that you have, right? That's a good way to think about life, I think. Well, it works that way with things like, why are we in school? Why are you studying stuff in school? Well, you're studying stuff because there is some value to it, right? Accumulating this knowledge gives you some power in life, whether that power is economic power by the kinds of degrees you're going to get and the kinds of jobs that makes available to you, or whether there's some practical considerations that it makes it easier to get through life. It gives you some practical advantage, Or maybe it's just that you're accumulating some knowledge that you can pass on to your kids eventually, right? And give them some benefits. There's always a benefit to learning things. And especially we identify some things in school that have more benefit than usual, right? And math is one of those things. It's not always easy to see where the benefit comes from, though, right? So I want to just give you a couple reasons why math is such an important thing to study. Well, for one thing, it's important to study because it makes you smarter to study it. I spend a lot of time researching the way that brains work. As a teacher, I think that's interesting to me. And it's interesting to me as somebody who values knowledge and wants to become smarter every day a little bit, right? I want to increase my own knowledge and become a more capable person. So we know that the way the brain works, the more that you challenge the brain to kind of flex its muscle, so to speak. It's like any other muscle when you're working out. Your brain becomes more capable through use. And we see this in all kinds of studies. People that are active using their brains throughout their lives have a dramatically lower chance of getting Alzheimer's or dementia later in life because their brains are more capable. If you do something that challenges your brain, like this is an odd one, but here's a good thing to do. If you're right-handed, this is going to sound really stupid, but this is absolutely true. If you're right-handed, use your left hand to try to eat dinner once a week. I'm serious. It's hard to do. Try to use your weak hand to eat dinner. It's very difficult to do, and that challenges your brain because your brain has a hard time controlling your muscles finely enough to get the food on your fork and up to your mouth, and don't stab yourself in the eye while you're doing it. But if you do something like that, where you try to like eat dinner once a week with your offhand, that really stresses your brain, and the extra connections that your brain makes to try to be able to accomplish that task can then get used to do things like foreign languages and mathematics, and it really does make a difference. Challenging your brain to do things that it's not comfortable with increases the number of axonic and dendritic connections that intersperse throughout your brain, and that's the mark of intelligence, right? So math is particularly good at that because it's very abstract and it's something that's not like everything else we do in everyday life. And so it forces you to make all these extra connections that literally make you more intelligent by doing it. By studying math, you're going to become better at anything else that you study also. Guarantee, I promise that's true. The research all shows that, okay? Puzzles, by the way, are also very good. So like another thing you could do is sometimes instead of playing video games sometime, do a puzzle or play a strategy game or something. Like anytime you're having to think hard about making a move or solving a visual puzzle, that also really strengthens your brain. Okay, so there's that part of it. There's that part of it that's really interesting about math. It's a valuable tool for you. But I got another one for you. And I'm just going to take a little time on Friday here. This is I'm going to sacrifice a little instructional time because I think this is something that's very interesting. So I want you to respond to me in chat here for a second. Just bear with me on this. Okay, I know this seems stupid, but there's a point to this. So if you've ever seen a line in everyday life, just type a yes in chat for me real quick. If you've ever seen a line before in your life, just type yes. Okay. If you've ever seen a point before, think about these geometry terms. If you've ever seen a point before in everyday life, just type yes in chat for me. Liars. You never have. And you never will. Because lines do not exist and points do not exist in our universe. What's the definition? No, I'm serious. I'll explain. You've never seen a line and you never will. You've never seen a point and you never could because they don't exist in our universe. Our universe has three extended dimensions and it has one time dimension, but we'll ignore that. It has three extended dimensions. I'll prove it to you. Put your hand in front of your face right now. Move it side to side. So left and right. That's one dimension, right? You can move side to side, left and right. Now go up and down. There's another dimension. Up and down is another dimension. Okay, now go forward and backward, away from you and towards you, right? There's another dimension. Those are our 3 dimensions. There's no other directions you could go. Those are the only 3 directions you can go that are at right angles to each other, right? Side to side is perpendicular to up and down, right? Up and down is perpendicular to front and back. Well, front and back is also perpendicular to side, isn't it? Right? Those lines I create when I do that. So there's only room in our universe for 3 different degrees of motion like that, 3 different types of motion that's going to always be perpendicular to the others. That's it. That's why we live in a 3-dimensional universe. Physicists are now suggesting that maybe our universe is what they call a bubble universe that's embedded within a multiverse. And it could be that there are other bubble universes that have different dimensionalities, that might have different numbers of dimensions. Perhaps they have 4 dimensions instead of 3, or 2 dimensions instead of 3, but ours has 3, okay? Well, in the 3-dimensional universe, let's consider a line for a second. How many dimensions is a line? Type a number in chat for me. And you could be wrong, but just what do you think? How many dimensions is a line? Okay, I can see why people would say both 1 and 2. Well, the answer is 1. The answer is 1 because a creature living on a 1-dimensional structure could only go, for example, if it was sitting in front of you, they could only go left and right. They have no other directions to go. They either go just along the string in one direction or along the line in the other direction, and that's it, right? And a point is 0-dimensional. Well, the problem is a 1-dimensional object cannot exist within a 3-dimensional universe. Everything in our universe has both length and width and depth, right? A line doesn't have that stuff. A line goes infinitely far in only one direction, either forward or backward in one direction. But what's the thickness of that line? It doesn't have any, right? It has no thickness because it only has one dimension. There is nothing in our universe that has no thickness. Nothing. Not even a beam of light. Nothing can have no thickness because at some point in our universe, if you shrink down small enough, there's something called the Planck length, 10 to the minus 46 meters, which is spectacularly small, but you can't go beyond that. You can't get any smaller. So you absolutely could never have anything in our universe that has no thickness to it, right? So there is no such thing as a line. There's no such thing as a point. There is no such thing in our universe as a plane, a 2-dimensional object. And yet we all know what we mean by those things, don't we? When I talk about a line, you guys all understand what that means. In your mind, you can build an accurate picture of what a line means, what it is, right? You can build an accurate picture of what a point is. So do they exist or don't they? Well, they don't exist in the universe, but they exist in our brains. And so they are useful, right? Now, how about this one? It's not just geometric things that don't exist. Nothing in math exists. Math is 100% unreal. Nothing about math is real at all. You might even think, well, Mr. Roy, 5 is real. No, it's not. 5 is just a concept. It's a concept to ascribe cardinality to something. 5 does not mean a thing. If you point at 5 rocks and say that's 5, well, no, it's not. That concept of 5 exists in your brain. The 5 is not a real thing, right? So even the parts of math that seem the most concrete and real are still completely unreal. They're still 100% abstract. How about that? That's pretty bizarre. Math is the only thing of its kind. It's the only thing that does not exist in reality. And yet, what do you think the best way to describe our universe is? Like, I've spent my entire academic career as studying physics, right? Physics is just the study of how does the universe work? How can we describe the way the universe works? How can we describe what happens if I launch a projectile into the air? Where's it going to land? Well, we can calculate exactly where it's going to land. What happens? How do we describe energy? How do we describe light waves traveling through space? All that stuff is physics, right? Well, what do you think physics is about 99% when you study physics? It's math. It's all math. It's crazy. The way that we describe the universe is completely dependent on math, and yet math isn't even real. Math is totally abstract. Okay, is this just blowing your minds? I mean, isn't that a bizarre concept, right? And so this whole thing that we learn, it's, this whole idea of this concept of math, I mean, you got to kind of square that for a second. You got to really think about that. I mean, it is completely in our brains, and yet it is the only way to accurately describe the universe. How crazy is that, right? So to me, that kind of gives math a new significance when you think about it in that light. I mean, studying math, it's beyond just studying like state capitals or something. I mean, it's not anything that's ever going to change. It's just this abstract reality. And if you ask mathematicians, do they invent or discover math? What do you think they say? And I'm talking about the best mathematicians in the world, the people that understand it better than anybody else on the planet. They all say the same thing. Weigh in on this. Here, let's do a little poll. I'll do a little poll here real quick. And if we don't get to any more math today, that's fine. This is a good enough topic that we need to talk about this. So you all have to tell me what you think about this. Everybody weigh in on that poll, please. What do you think? Is math discovered or invented? If it's discovered, it means it's already there and we're just discovering it. If it's invented, it means that we're coming up with the math in our minds. We're creating the math. Everybody take a vote. It's anonymous. No one will see your. Okay. Okay, I see invented. There's another invented. Okay. Okay. Add 2 more to invented. So it's really 13-2. All right, here's what I'll say about that. Liars again. That's not what mathematicians think. They unanimously, all these top mathematicians say, no, it's not invented, it's discovered. It can't be any different. There's no other way math could be. We're not inventing it, we're just discovering it as we go along. And they'll say something else even. They say, and this is where it gets really bizarre, but it gets this, I mean, this is crazy stuff, but it ought to give you a new appreciation for the math that you're learning. They even say that if you were to go to these other universes I spoke of, these other, that are in our multiverse, assuming they exist, and we don't know that for sure, but physicists are becoming more convinced that that's the way it probably is. If you were to go to these other universes where maybe they were vastly different, maybe let's just take, for example, a universe that had 4 dimensions instead of 3, the creatures would look very different, right? They would be very different kinds of creatures. But if there were some 4-dimensional students sitting in some bizarre 4-dimensional teacher's class learning about math like you guys are, what these mathematicians and physicists say is that the math would be exactly the same. It wouldn't be any different. There's no possibility for the math even being different in different universes. The math is the math is the math. It could not change. It's always the same. How about that one? Isn't that crazy? I mean, if there is some distant galaxy in our universe and students, if our universe is infinite, by the way, there is 100% chance that there is somebody having this exact conversation right now. I'll get into that some other Friday. How about? There's another group of students having this exact conversation right now if our universe is infinite. And I'll defend that. I'm 100% true, 100% right that that's 100% correct, but I'm not going to defend that till some other Friday. We'll save that for later. But then they would be studying the same thing. So then James has a good question. So then where and when does the concept of math originate? Well, the concept of math just originates when people become intelligent enough to consider math, right? To consider the abstraction of math. And how about this one? If you look back, even just on Earth, let's not even focus on these other universes. Let's just think about Earth for a second. If you look back at the way people developed mathematical thought in different parts of the world before they could even communicate with each other, when they were geographically isolated, right? What do you see? Was the math the same or different? Exactly the same. They might use different symbols, right? They have different languages, so they might use different symbols to represent the concepts, but the concepts are exactly the same. There's no other way to come up with a concept of 2 than 2, is there? You might call it something else. Maybe you call it flam. I don't know, but it means the same thing, right? It still represents the same concept for people, right? If I point to 2 rocks, whether I call it flam or 2, I mean, it just means 2, right? It means the same thing. Okay, and that leads to other higher math concepts. And really, all these math concepts eventually, they just really start with arithmetic. And then as we branch out our thinking from there, we discover more and more different kinds of mathematical relationships, right? So that's pretty crazy that the stuff you're learning, not only does it transcend culture on Earth, it's going to be the same every place in the world. It, in fact, would be the same at any location in our universe and even in any possible universe. That's crazy. There's nothing else that you could ever learn that is that global, right? Anything else you learn is going to be unique to probably just your own location, certainly your own universe, right? So math is pretty unique, which is yet another reason why it's really something that people should experience, because there's some fundamental truth there when you study math that's different than the other things you study. There's something there that has an absolute truth to it that's different, right? There's something unique and powerful about that. So hopefully that allows you to think about math a little differently than you have in the past. All right, so we don't have much time, but let's reel this back in and let's look at just a brief example of how this stuff works. How can we take, excuse me, how can we take an abstract concept in math, and everything we've learned this year has been completely abstract, and how can we apply that to something on Earth that has completely non-mathematical implications, right? We're just starting to be able to do that. You've never had enough math available to you. You haven't known enough mathematics or mastered enough mathematics to really do anything with it. And even now, you can't do much with algebra, right? Once you get to calculus, then it just opens up and you start to see, wow, okay, now these connections become more obvious, and you start to see all these applications that come out that are super interesting. But until you get there, you don't see much of it. Well, here's just one little example. Let's look at the screen up here. Let's look at this example. It just looks like a boring old word problem. But try to see this through a different lens here. Try to think about this as a concept that's predicting mathematically a result that is an actual real world result, okay? So say you've got 220 feet of fencing to enclose a rectangular garden, right? What dimensions of the rectangle would give the maximum area? And what is the area? Now think about the ways you could go about solving this problem, right? All of them depend a little bit on math, but I mean, you could just build a whole bunch of different gardens and measure the results and see which one has the biggest area, for example, right? How would you ever know, though, that the result that you got was the absolute biggest? You could try trial and error and just doing some calculations. But is there a way we could tie a math concept into this that's going to convince us absolutely that, okay, we're done. We got the answer. There's no other possible answer. This is it, right? That's what math does for us. That abstraction, we can apply it here and we can convince ourselves logically, mathematically, that we're getting the right answer because it fits the math, okay? All right, so we'll just get a start on this. We're probably not even going to finish it, but that's okay. When are we out of here, by the way? We're out of here for, we might get through this one. We'll see. If we don't, we don't. So let's start off with maybe just a rectangle. For this is our garden. Okay. So here's our garden. We want to come up with an area, right? How do we calculate the area of a rectangle? Just either say it out loud or type it in chat. Think back to geometry. How do you calculate the area of any rectangle? Okay, length times width. Yeah, we'd all agree length times width. Okay, let's give this. Now, here's something mathematical we can do. Already we can come up with something that's a little bit abstract. Now, we don't know what the dimensions of our garden are going to be, right? So we're going to go ahead and we're going to call them unknowns, and we could give them a variable. I'm going to call that x, let's say, okay? And maybe we'll add another one here in a second. Now, what about, we have another statement here, though. It tells us that we're going to use 220 feet of fencing to enclose a rectangular garden. If our goal was to build a garden with the maximum area, and I wasn't given any other information, heck, I know what I'd do. I would just make my garden, the dimensions, infinity by infinity, and I'd have the biggest possible garden, right? Okay, that would work great. But we do have a constraint here. In math, we use the word constraint. We have a limitation. We only have 220 feet of fencing, and so infinity by infinity is not an option, right? We only have 220 feet of fencing to use. What's the geometry word that we use to describe the distance around an object like that, around a rectangle? In this case, that's our fence goes around the edge of this thing, right? I almost said the word. The fencing goes around the blank of the garden. What's the perimeter? Sure, right? So we know that our perimeter in this case equals 220 feet, right? Everybody agree? Okay, well, if the area is going to be the width times the length, and if the perimeter is 220, I want to be able to come up with a name for this side of my rectangle here, the length for my rectangle. And my goal is I'd really like to use the same variable x. Okay, if I can do that, I can come up with a function here. Area is length times width. I could multiply x times whatever my length is going to be to get my area function that's going to calculate an output of area, right? Okay, let's be a little tricky about this. Let's think about this. If the perimeter is 220, then what would half the perimeter be? What if I started in the upper left corner and I walked all the way down to the lower right corner? What is that green distance if the total perimeter is 220? Okay, everybody agree it's 110. Okay, it's 110. So then if that whole green distance is 110 and that part of the green distance that represents the width of the rectangle is x, what would be left over for the length then? What would the length be? If the whole green distance was 110 and x of it is the width, how much of it is left over for the length? Okay, it's the 110. It's the green distance minus the part that's already been used up by x, right? So it would just be 110 minus x. Everybody agree? There's another way we could do that by calling it y and making a substitution, but we don't need to get that complicated. We can just think of it this way. This is fine, right? Maybe later on for a different problem we'll come back and we'll look at starting off with two variables and making a substitution. But let's avoid that for now. We don't need to. So then our area is just the width times the length you told me, and the length is 110 minus x, right? Okay, so area equals x times the quantity 110 minus x. Well, we only have one kind of input there. It's just an x. So I could change this and I could make it look like a function now. I could use function notation. So this tells me that I'm calculating area as a function of x. I'm inputting x values and this equation is outputting area values, right? Okay, already that's pretty interesting what we're able to do there, right? I don't know what x is. X is the width of my garden, but whatever it is, whatever the width is, I can now calculate the entire area just from the width by using a little math, right? So let's distribute the x, and let's go ahead and put the x squared term first, right? So if I distribute the x, I just get 110x minus x squared. Let's put the x squared term first, and now we've got, let me give myself just a little bit more room here. Now I've got negative x squared plus 110x, and that's my area function. Well, now hold on, that looks familiar, right? That looks familiar. This just happens to match, and that's why I picked this example, obviously. That happens to match what we're talking about, right? That is in the form of a quadratic function in standard form. Everybody see that? It fits the form ax squared plus bx plus c, right? So this weird concept we've been talking about that, that involves parabolas and vertices. Yeah, vertices that's plural for vertex, right? Involves, vertex and parabolas and vertical dilation factors and all that totally abstract stuff that we've been talking about. No connection to reality, right? Well, look at that. That matches the function that predicts area for us, right? That matches this standard form of a quadratic function. Okay, so what are the values of a, b, and c for us? What's the value of a for our quadratic function in standard form? And it doesn't matter that it's an a instead of an f, right? A is just, I just picked a for area, right? F just stands for function, I guess, but it could be anything. It doesn't have to be f of x. I can call it a of x. What's my value for a? Type it in chat. For my function. And remember, a is just the coefficient of x squared, whatever's being multiplied by x squared. So what's a? Okay, -1. All right, I'll buy that. What's b? Okay, good. I'll buy that too. And what's c? Yeah, it's 0. Nothing's being added, so c is equal to 0. Okay. Well, this looks like a quadratic function where a is -1, b is 110, and c is 0. Now, I want you to make a prediction for me here. This is something in math. Now, you can start to make a really powerful connection here. Okay, if we were to graph this thing, and you always want to think about these functions. If I build a function, just think about what its graph would look like, right? If I graph something, I'm graphing it in the xy plane, but instead of y, our y here, we're using a fancy name for y. It's just a of x, right? Remember, f of x is just a fancy name for y. Well, this is just a of x, another fancy name for y. So I'm graphing horizontal axis, I'm graphing values of x. My vertical components are going to be values of area. Okay, this is going to be a parabola, isn't it? If I graph this function in the xy plane, I know I'm going to get a parabola. All quadratic functions give us parabolas. In chat, tell me, is this parabola that I'm graphing going to open up or down? Okay, good. I'm seeing down. And I know what you're looking at. You're saying a is negative, so it's going to open down. You're correct, right? So if I were to graph this parabola, it's going to look something, I don't know exactly what it looks like, but something like that, okay? And let's think what the ordered pairs on this parabola represent. Like, let's just say I'm going to pick x equals 10, okay? I'm going to plug 10 into my function. Well, what's a of 10 going to give me? I'm going to get negative, for my x, I'm going to plug in a 10, so I get negative 10 squared plus 110 times, instead of an x, I'm going to plug in a 10. That's going to give me negative 100 plus 1100 is just 1000 is my result. So if I plug in a 10, it outputs 1000. Okay, I want you to tell me now, what's the physical significance of that 10? That's a value of x, right? So in terms of my problem up here, what does x represent? If you look at my picture that we all drew, right, of that rectangle. So what does the 10 represent here? Type it in. I've got this coordinate on my parabola. The x coordinate is a 10. What does that 10 stand for? We're making a connection here between this abstract parabola, totally abstract, and our physical garden that we're going to build. What does that 10 mean? Right, that's an x coordinate, isn't it? So that's a value of x. What is x standing for in my picture? What does x represent? Yeah, it's the width of the garden, isn't it? Right, good. So 10 represents a width of 10 feet, okay? Okay, what does the 1,000 represent? That's my y coordinate. Now my y is really a function here. It's a of x. So what does a stand for? That's my output. What does a stand for? What's the 1,000 telling me? If I make a garden with a width of 10, that's what the 10 stands for. What does the 1,000 stand for? That's the y coordinate, which is always y is the output, right? So what's the output of my function? My function is a of x, right? I plugged the 10 into the function a of x. What is a of x telling me? How did we get this a of x originally? I never wrote this down, but I should have. You guys told me that area equals length times width. That's how we came up with that function. What am I oh, it's area. Good. Okay, so that's area, isn't it? Right, so this is telling me that my garden has area of 1,000 square feet, right? Well, that's just one possible point. I could pick any point on this parabola, and it's going to correspond to the area that I get for that width. Okay, now I know we got to go, but give me just 30 more seconds here, and then we'll wrap this up. So do you see a place on this parabola where I could be absolutely certain that my area, the y-coordinate, is going to be the biggest possible area? Where would that be on my parabola? What do I call that point where I know I'm getting the maximum value for my function, for the output? Yeah, look at that. If I could find the vertex is exactly what I'm looking for, isn't it? That vertex is going to give me the maximum possible area and the width that produces that. That's pretty cool, right? We know that for a fact because we know that the vertex is the maximum value for a quadratic function that opens down, right? A parabola that opens down. Okay, we'll wrap this up next time, but does that make a connection for you? Isn't that kind of cool how we can take all that abstract stuff we've learned, no connection to the real world, and that's telling us how to build the biggest garden, right? Okay, have a great weekend. I'm here after school if you need me. Go enjoy the sunshine. Think about math a little bit this weekend. Have a good one.